Hey everyone, welcome back. This is Joe with Pro Flight Trainer here with my first video in FSX, and this is the FSX. This is the Bell 412, the Hover Control Bell 412 for FSX, and this was originally a Microsoft Flight Simulator 2004 A Century of Flight model that was then later updated to FSX. So, old model we're looking at today. But it's still a popular one now. Alright, so we're going to jump right into it, and just to give you an idea of what we're testing, it's the same. If you've seen any of my other videos, we're using the same parameters. So we're back at Henderson Executive Airport. The elevation is about 2,500 feet, 20 degrees Celsius outside, winds calm, and the aircraft weight we're sitting on here on 35 right at about 9,000 pounds. So same test parameters as we tested the X-Trident Bell 412 at. And similar to what we tested the DCS UH-1. Alright, so we're going to start with a hover power check, and still don't have much hover performance data for the 412, so what we're going to do is we're just going to test general handling and see what kind of power we're using. So the X-Trident 412 hovered around 30% torque, so we're going to see what this one hovers at. So we're going to bring some power in, and I'm habitually putting in some left pedal here, see what comes up. Alright, about 25. Okay, looks like we're hovering just over 25% torque. I'll look in here real quick. Yeah, so about 26% torque looks like what we're hovering at, which is about 4% lower than the X-Trident model hovered at, which it's actually not that uncommon to see a discrepancy like that between airframes. So we'll call those two aircraft similar in that respect, and how that compares to an actual 412, I don't know, because no one's let me fly theirs yet. Just dropping a hint to any 412 operators out there who might be watching this. I would like to fly your helicopter. Okay, I'll drop the hint. I want to fly your helicopter. Okay, anyway. Back to what we were doing. Okay, so one thing to note, looking at the panel here, a key difference between this model and the X-Trident model that I need to highlight here is the lack of a selection for AP1 and AP2, or HP1 and HP2, depending on which variant of the 412 you're looking at, or what avionics you have installed. So I'm assuming this model was created without the consideration for any sort of artificial stabilization, even though some of those things are shown here. So you can see a panel for the autopilot there, and you can see lots of avionics modeled, but so the autopilot here, not really much you can do with it. It's more cosmetic. This panel here, again, cosmetic. So I'm going to assume these systems are in-op. Excuse me, here we go. We do have AP1 and AP2 buttons, however, they don't do anything. They're cosmetic. They're just textures. So we're going to assume that these are inoperative, or modeled. This model is modeled without them. Okay. All right. So the next thing we're going to do is a no pedal takeoff. So basically, we're going to check for torque effect. So I'm going to center the pedals, and we're going to pick the aircraft up and see what we get. So what we're expecting to see is the nose to turn, in this case, to the right, opposite of the rotation of the main rotor. And we just want to see if there's torque effect model. So we're going to bring some power in, again, with the my feet on the floor. We're at 20% torque, which this is about where the X-Trident model started to rotate. We're starting to creep the nose around to the right, so that's a good sign that we have torque effect model. Bringing in some more power. We're at 25% torque. Alright, coming up to hover power here. Alright, so we're picking up an okay rate of turn here. A little bit of aft cyclic to keep the nose from pitching over. Alright, so we're at a hover, and that's actually a pretty slow rate of turn. It's I would expect a little bit more for an aircraft that doesn't have any sort of artificial or automatic flight stabilization. I would expect a little bit more than this. This just to me feels like a right pedal turn, to be honest with you. like something that's intentional, not something that's this feels like a control input, because I could pretty easily get this thing back on the ground without damaging the aircraft. As you can see, during this I've been able to keep it right over the numbers here. So yes, torque effect is modeled. Is it realistic? I'm leaning towards no. So probably not going to give full points for that one. Okay. Well, let's test one more thing. I'm going to bring in some more power. So we're at just 26% torque. We're going to bring in 10% over that to see if we get an increase in our rate of turn here. All right, so bringing it in. So it looks like, yep, looks like it is starting to speed up a little bit. Was it? Am I just imagining that? Bring in more power. Okay, yeah, okay, so there's a definite increase in rate of turn now. Okay. So, yes, with more power we get a higher rate of turn, but aircraft doesn't really seem to want to go anywhere. So, you can see we are just pivoting around a point. We're not really moving. Cyclic I'm not doing much with, so that's kind of interesting, that this aircraft is that stable with, goodness, about 180 degrees a second. So that's okay. So before you guys get sick, I'm gonna lower the collective. So I like that we get an increase in the rate of turn with an increase of power, but it actually seems to be more altitude driven, not power driven, because as we descended there, we slowed down like almost immediately. But at that low power setting, as I descended, that rate of turn stopped almost completely. So that's actually pretty promising. So I like the response. However, the rate of turn, I think, especially at lower power settings, would probably be a little bit more. Especially since the inherent stability of the aircraft, I think, is suspect. Because with all that, without touching the pedals, I've been able to bring us back over to the numbers, even after all that crazy spinning. Bring us back over to the numbers relatively easily. So I think that's probably not the most realistic. But also keeping in mind this was originally a Microsoft Flight Simulator 2004 Century of Flight model. So for Microsoft for FS 2004, that's actually pretty darn good. Alright, so next thing we're going to do is we're going to just take note of how much power it takes to, how much pedal it takes just to maintain a hover, and we're going to do some hovering turns here. Make sure our our pedal input is realistic. Okay, so coming off the ground, and you gotta forgive me, I very rarely fly FSX. Actually, I had to reinstall FSX to do this video because I'm very rarely in this sim. Alright, so looking down at the feet, not a whole lot of pedal required to maintain my heading. Yeah, I would expect a little bit more pedal. So this would suggest that we have some sort of artificial stabilization, which I'm not sure that we do. Especially based on the test we just did. So I would expect to see a little bit more left pedal required to maintain this heading. But we're going to keep that in mind when we do this at a higher gross weight. So now what we're going to do is we're going to start a left-hand turn. So I'm going to add a little bit of pressure on the left pedal. Get this turn going. And that's about right. As far as the pedal required to initiate the turn, I kind of feel like we should have had a little bit more left pedal in to maintain our heading, but this feels pretty good. Alright, I'm going to ease up off the left pedal. Again, it doesn't take much left pedal to maintain your heading at a hover here. And what we will get into a little later is cyclic input, and it takes a lot more, much more cyclic input than I'm used to maintain a hover, which is kind of weird. But we'll talk about this later because there's two parts to that. One, it takes more input to get the aircraft to do what you want, but once you get the aircraft steady, it doesn't really take much to keep it there. And when I say much, I mean anything. So that's kind of weird. But we're talking about pedals right now, so we're going to stay focused on the pedals. Now we're going to go to the right. So I'm going to add, and in this case, I actually feel like I'm adding the right pedal. And we can look down on the ground there. So instead of just relaxing on the left pedal, I actually have a tad bit of right pedal in. Actually, no, I don't. That's about neutral. So that I would not say is realistic. I mean, if we are talking about an aircraft that doesn't need, that doesn't have any sort of artificial stabilization, I would expect to need to relax off the left pedal, not go neutral to start a right-hand turn. So I'm not sure. When I say I'm not sure, I'm just going to say it. I'm not going to give full points for that one, because that seems not like it's not very realistic. Okay. Next thing we're going to do is we're going to, while we're still looking at the pedals, we're going to go full throw in the pedals. I expect to see a pretty rapid rate of turn here with full pedal and we're going to do the same thing to the right. And again, I expect to see the aircraft whip around. Okay, so slide back over to the center line to give myself a good point of reference. There we go. Alright, and throw in some left pedal in there. That was a really big, that was pretty sluggish, actually. Kind of took a little while for the aircraft to catch up to what I was doing. Let's try that one more time, and this time I'm going to look at the pedals here. Alright, so I'm going to go full left pedal. Yeah, kind of see how it just kind of ramps up. Alright, I'm going to stop it. And we're going to try that again to the right. I expect to see a little bit, expect it to be a little bit more responsive to a sudden rapid application of full pedal here. So, because there's almost a pause, and when I say almost, I mean there is a pause. We'll see if it does the same thing to the right here. So putting in full right pedal. Okay, so the right pedal application was almost instantaneous. And pulling in left pedal, okay, full left pedal, and it took a couple revolutions for that to stop. It's almost as if we got into some unanticipated right yaw. But it was anticipated because I caused it. We're going to try that right pedal one more time. Because that was interesting. And we're going to go left first, and then right, because that was pretty interesting why there was such a sudden delay. Maybe, let's see here. All right, so I'm going to apply that full left pedal a little bit slower and see what happens. So, jamming in full left pedal. It still takes a little while for that to build up while going to the left, but going to the right, we stabilize here. Going to the right is almost instantaneous. It still takes a little while to build up, which makes sense. It also takes a lot longer to stop a right-hand turn than it does a left-hand turn. So it's not unrealistic for it to be a slower build-up, like with the right-hand turn, but with the left-hand, there's almost a there's this hesitation, like the aircraft is unsure of what you just did. So that's kind of weird. And another thing that's really weird is that I can stop a right turn, or excuse me, a turn to the left almost immediately with the application of right pedal. So I'm going to pick up our full left pedal and then stop it with full right. So that's about what I expect. And then we're going to go full right pedal. Alright, and trying to stop it with full left, we get almost 2 full revolutions. Actually, just over 2 revolutions before that aircraft responds. So that's kind of weird to me. I'm not sure what that's all about. So there's a lot of things in there that are just kind of weird that I can't give full points for. Alright, we're going to go into level flight. So we're going to take off here and make a turn to the south into my regular test flight area. And we're going to look at a couple of things. Alright, so what we're going to look at is we're going to do some turns, and we're going to see what kind of pedal coordination we need to maintain trim. Alright, so get the aircraft in trim here, and actually I'm going to take off power. So we should be somewhat in about cruise power here. And to keep us in trim, I've actually got more left pedal in than we did at a hover to keep us in trim here. So that's actually kind of bizarre. At just over 100 knots, I would expect to see some right pedal in there to keep us in trim, but that's okay. Well, it's not okay. I'm going to dock points for that. But we're going to start a turn here and see what we need to do to keep this in trim. And apparently nothing is what we need to do. That trim ball doesn't want to go anywhere. Oh, here we go. Now we're starting to get some movement. Okay. So maybe a little bit more left pedal. So we're already at a... Oh, I'm also slowing down here. Sorry about that. Cross-check's getting slow because I got my face smashed into the instrument panel. Actually, to be honest with you, it doesn't really seem like the aircraft cares what I do. So the trim ball just eventually finds its way back to center. So that's interesting. I'll keep my airspeed up. Yeah, so I'm going to go neutral, see what happens. So there's an initial offset of the trim ball, and then the trim ball just kind of finds its way back to center. Well, maybe not completely. Okay, so finally we can get an uncoordinated turn here. Oh, well, maybe not. So it kind of seems like the trim ball just kind of goes back to center whenever, but it does tend to favor the left pedal during a turn, at least to turn to the left. So we're going to go to the right and see what happens. Okay, with a right-hand turn. Again, looks like it wants the left pedal to stay in trim, but not a lot. So I'm here, I've got the pedals pretty much neutral. And trim ball seems to wants to stay put. I'm going to increase the angle of bank this here as an experiment. So I'm going to slow down a little bit. I'm already slowed down, looks pretty good. But yeah, that trim ball doesn't really seem to want to go far from home there. Switching over to the left-hand turn. Still wants to favor the left pedal a little bit. Alright, so that's kind of weird. I expect a little bit more right pedal, especially in cruise, but this seems to want to favor left pedal. And I say that now, but we're at neutral pedals here in cruise flight, back at 100 knots, and the trim ball's almost centered. So yeah, it looks like it still favors left pedal in cruise, which I would expect the opposite. With the vertical fin offloading the tail and the slipstream, I would expect a little bit of a right pedal in cruise to keep it in trim. So, nah, not too crazy about that. Okay, back at 3.5 left, looking at my torque. So we burned off some gas. So we're hovering right about 25% torque. Oops, sorry. Again, hard to hover when you have your face smashed into the instrument panel. Actually, it looks like we're still hovering right around 25-26% torque. And not a lot of pedal. Just about an inch and a half, maybe 2 inches max of displacement. But I would say it's probably about an inch of displacement. Okay? So looking at pedals, yep, that's what we got here at IGE Hover. So I'm going to put the aircraft down, and we're going to load it up. My hovering is so terrible in FSX. Alright. Alright, so now what we're going to do is we're going to load the aircraft up, and we're going to use the same weight that we did for the X-Trident model. Hang on, there we go. So, yeah, we burned off a lot of fuel. We're going to bring this up to, not sure what happened there. Oh, there we go. Let's look over here. That was weird. All right. So we're going to load up the aircraft to the same weight that we used in the X-Trident model. So we're going to bring the aircraft up to about 11,000 pounds. So we're going to add some weight. And try to get this thing up to 11,000 pounds as close as we can. So we need a little bit more. Okay, there we go. All right, so you can see we load this thing up to about 11,000 pounds, which is the same as what we used for the X-Trident. And now we're going to test and see what the differences are. Okay, so I have the old hover power setting in as far as the pedals go. And so we're going to pick up to a hover again and see how well the model does. Alright, so picking up on the collective. So old hover power was about 27% torque. So we're passing through 27 now. Nothing. Aircraft's actually starting to move just a little bit, so it's getting pretty light on the skids. We're at 30% torque. Aircraft wants to move. Okay. Looking good. So we're coming up we're off the ground. Just at 31% torque. 31, actually went closer to 33-ish. So 32, 33% torque. The nose came to the right a little bit. You can see we have the same displacement as we did for, well, maybe I did give it a little bit more left pedal. So about the same displacement, not much more. I think I gave it a little bit more out of habit, as we did at 9,000 pounds. So I would expect a lot more this close to max gross weight than that sort of displacement. So that's I think it's pretty safe to say that that's not very realistic. I mean, no data or not. We just increased the weight by literally a ton, by 2,000 pounds, and very little extra pedal is needed. And that's almost, to be honest with you, it feels about the same as it did at 9,000 pounds as far as pedals go. So I would expect there to be much more of a difference between pedal input required. Again, I know it's a FS 2004 model, but we got to hold everybody to the same standard. So yeah, can't give points for that one, guys. Okay, put the aircraft back down just for a second. Alright, so just for fun, I brought it back down to 9,000 pounds because we had to burn a little gas over earlier. So I brought it back to 9,000 pounds. And we're back in, so we're going to keep that same pedal setting that I had for 11,000 pounds. We're going to pick the aircraft up. Again, we're looking for just to see if the pedal requirement changes. So we came off the ground at 9,000 earlier in our test today at 27% torque, so we're right at 27%. And pedals are just where they were a second ago, okay, at 11,000 pounds, and the nose isn't going anywhere. So that to me says there is no difference as far as pedal input required for close to max gross weight for takeoff and at our regular testing weight. And I suspect that that'll be the same if we go back to a very low weight. So actually, you know what? I wouldn't be doing my job if I didn't test it. All right, so we're going to put it back on the ground. And actually, as I lowered the collective there, I would have expected the nose to go to the left a little bit, and it didn't. So let's test it in full here. So we're going to go back to our menu here. Fuel and payload. And we're going to change that payload. So we're going to remove all that weight. Okay, all that weight is gone. So now we're about 8,000 pounds, so we're 1,000 pounds lighter than we were earlier. So 1,000 pounds lighter than we have been throughout this entire test so far. And we're going to see, again, same pedal position. Bringing the power up, and now I'm expecting to come off the ground probably 1,000 pounds lighter, probably closer to 20% torque, maybe 25-ish, 23, 25% torque. So there's 25, and yep, off the ground, here we go. Again, same pedal setting. Haven't touched the pedal, my feet are on the floor. 25% torque, and nose doesn't want to go anywhere. Okay, so we've gone from 8,000 to 11,000 pounds, and we're using the same pedal setting. So alright, next thing we're going to do is we're going to test some torque and RPM influence. So we're going to come back over here to this nice little open area and do the hover test first. So basically we're going to apply pedal and see how that influences the torque. So from a hover here, and we're still at 8,000 pounds-ish, so we've got plenty of power to work with. I'm going to jam in some pedal, and we're going to see if that affects our torque in any way. And I was actually keeping an eye on this earlier when we were doing the max pedal tests, and I kind of already know where this is going to end up. Alright, so as I jam in this pedal, I'm expecting to see a torque spike, because we're going to increase drag on the drivetrain, and that's going to demand more power from the system, and all that fun stuff. So here we go, a little bit of left pedal, and we saw nothing. Which I suspected because I was looking at this earlier. And if I jam in some right pedal, saw a little bit of torque fluctuation, but that's because I adjusted the collective. So I'm going to take my hand off the collective here and jam on that right pedal, and nothing. So I should have saw the torque dip a little bit there, but nothing. And even when I jammed the full left pedal in there to arrest that, I didn't get anything. We're going to test this. We're going to test some more here in cruise flight. So can't get points for that, but we do have some more things to look at. So we're also should have saw some RPM changes and all that. I mean, governors are good, but we should have seen the governor kick in and try to maintain that rotor RPM. So that's kind of a, can't really give points for that one either. Alright, so we're going to be established in cruise flight here. I'm going to level off. I'm not going to climb too high because we don't need to. And again, in cruise flight, we should see some changes in torque as I play with the pedals here. But those needles are solid. The only thing that seems to affect those needles on the torque gauge is the collective. And RPM as well. I'm not getting anything out of that. So, but collective moves them all day. But collective doesn't affect trim any, so we should be seeing a massive, not massive, but we should see a pretty significant change in trim right now. And I'm going almost full up, full down on the collective here. I'm starting to see a little bit of torque influence on the trim ball here? Not much. But I'm not seeing anything with the pedal, so that's, can't give points for that one. Alright, we're going to move on to the next part. So we're going to look at RPM. So we're already in cruise flight here, albeit low level, but we're still in cruise flight. And I'm going to do a quick stop and see if I can't get the RPM to increase on me. So basically what I'm going to do is I'm going to expose more of the lower half of the rotor system to this oncoming air. It's going to cone, it should cone, theoretically, cone a little bit, bringing the center of momentum. We're basically talking about conservation of angular momentum. You guys don't care about the specifics. Alright, so I'm going to bring the collective down, bring the cyclic back. Alright, not my best, because we ballooned quite a bit, but I'm not seeing any fluctuations in on the triple tack here, and really no indication that I did anything with the cyclic. We should have saw at least a little bit of rise in rotor RPM, because I had offloaded the, I had reduced the collective, so it took a lot of pitch out of the blades, but still brought the cyclic back, which should have caused at least a spike in rotor RPM. I'm going to try it again. I need to slow down here for a minute, because doing that 80 knots is going to cause me to balloon up pretty rapidly, but almost got the collective to the floor here. Alright, so about here, we're going to bring the cyclic back. Alright, definitely should have saw a little bit of rise in torque there, or not torque, but rotor RPM. But those needles stay right there with virtually no changes. Yeah, not much we can do about that as far as points wise. Let's go ahead and go back to our test flight area. Actually, we can do this in a pattern here. I don't know why I keep looking for traffic. There's nobody here with me. Sorry, I can't help it. So I'm just going to see if there's anything I can do to get that triple tack to fluctuate as far as manipulating flight controls. Because the quick stop didn't really do much. So collective all the way down, cyclic all the way back, nothing. I mean, short of rolling the throttle off, I don't think that I can get any sort of RPM fluctuation with the cyclic. I mean, that was a pretty rapid cyclic application with a pretty good amount of airspeed. I couldn't get anything out of it. Let's try some banking turns here. Alright, so 80 knots. I'm going to do this to the left, so I'm going to lower the collective a little bit. Alright, definitely should have saw something on that one. I hadn't zeroed out my airspeed. I mean, unrealistically quickly. But it doesn't look like we're getting any RPM fluctuation. So, sorry guys, couldn't get anything out of it. So that's going to be, I don't know why I'm apologizing to you guys all the time. I don't think you guys care about that. But, yeah, can't get much out of that, so no points for that. Alright, next thing we're going to test is needle separation. This one's going to be a little tricky because I think the way this thing is set up, this may cause some problems. So we're going to come over to the runway here. Runway 35 right will do. This feels so sloppy. Okay. So we're going to try from a hover. I'm going to roll the throttle off and see, and we're going to keep an eye on our triple tack there, and we're going to see how that gauge behaves. So what we're expecting to see is I wasn't expecting that. I'm not sure what I did. I think I may have rolled the throttle off inadvertently. Kind of weird. Okay. I didn't think I rolled the throttle off, but okay, whatever. Alright, so actually what I want to do is bring up the throttle. So the throttles in this model aren't animated here on the collective. So what I can do is, as soon as I find it, nope, wrong one. Looking for, there it is. Okay, so I'm going to see if this works. Nope, that doesn't show anything. Okay, so you guys just have to take my word for it. So you can see as I move the throttle here. So on flat pitch, yeah, it looks like we're getting a good needle split. Sort of. Alright, so I'm rolling the throttle back a little bit, and it looks like engine 1 and 2 needles are reducing, but rotor RPM is still at 100%, which is kind of weird at flat pitch. I'm going to see how far back I can go. Okay, so that's definitely unrealistic. With both engines less than 80% and the rotor RPM still at 100. Yeah, this is weird. We're down to 70%. Rotor RPM still at 100. So we're definitely getting a needle split. However, I would expect the rotor RPM to follow the N2 needles there, and they are not. Which is weird. Okay, so the throttle. Okay, so that was peculiar. Okay, so I brought the throttle. When I got the throttle all the way to the stop, engines 1 and 2 went all the way back to 100% again, so that was kind of weird. So, so rolling it to, nope. That's some strange behavior. So we're getting a needle split, but it's the wrong kind of needle split, because the rotor seems to be powered by sheer will instead of the engines when I manipulate the throttle, so that's kind of strange. Alright, let's come to a hover and see what we can get. Alright. So coming back up to a hover. And yes, I know this is an old model, and he was working with the best code he had at the time, so it's not going to be completely realistic, but we're keeping everything to the same standards here, guys. It's the test isn't adapted for different eras. It's the same test criteria for each model. Alright, so we're going to try a hovering auto rotation here, so we're rolling the throttle off. Okay, so now that's kind of weird. Now we got no needle split, and both the rotor and the engine needles went down simultaneously, which I would expect the rotor to come down faster at a hovering auto, but I would still expect to see the engine needles come down a little bit faster than the rotor RPM. So that's kind of weird. Okay, let me get the RPM back up to fly. I'm going to try it from cruise flight here. Alright, looks like we got everything back up. Should be able to climb high enough. If I can get 60 knots out of it before we're mid-field, I'm going to go ahead and start an auto. Actually, no, I'm not, because this thing, I think, tends to float a little bit. So we're going to come around to the left here and continue to climb. And we're going to start our auto rotation, or attempted auto rotation. We'll use 3.6 right, 3.5 left, because I think it's a little longer. That'll give us a little bit more space to work with. So, based on what we saw at flat pitch ground and at a hover, I am not sure what I'm going to see when we roll this throttle off. Okay, so I'm going to slow down just a little bit. we're going to enter this auto rotation around 70 knots-ish. There we go, going back around. Speed's about where I want it, about 5 knots faster than what I stated, but plus or minus 5, that's not too bad. Okay, there we go. It's about 70 knots. Coming around to 3.5 left. Alright, I'm going to roll the throttle off. Roll the throttle to idle, excuse me. Selector's going down. Okay, so we got some odd behavior there. So looks like we started to get a needle split. And then, okay, so I had the throttle idle and the needles married. I'm going to crack the throttle open just a little bit, and it looks like we're getting a needle split then. But it's a reluctant needle split. I'll roll the throttle. Actually, it seems like the more I roll the throttle on, the greater the needle split. That's kind of strange. I'm going to terminate this with power. Oops. Actually, looks like I'm just going to crash, but I turn the crashes off because I don't want to keep resetting this all the time. So that was weird. So I'm going to try that one more time. And instead of rolling the throttle all the way to idle, what I'm going to do is I'm going to roll the throttle what I think is halfway to see if we can't get a clean needle split. Because it looks like that's what it takes. Because if you go all the way to idle, the needles want to marry back up again, which is extremely unrealistic, so already no points. But I want to see what it actually takes to get this thing to behave somewhat normally. And I think that may be some coding thing with the 212. Not exactly sure, to be honest with you, but we're gonna test it again anyway and see what we get. Bring it back to about 60 knots here, so we can climb a little faster. Okay, so we're going to try this one more time, and instead of going all the way to idle, I'm just going to roll it back to what I think is halfway and see what that gives me. Okay, 70 knots is the entry speed I wanted. Alright, and going to halfway. Collector's going down. It's a little late on the collective there because I was focusing on the needles. Okay, so we have a needles married back up again. I'm going to roll the throttle off a little bit more. So maybe I didn't get halfway. Okay, I'm going to leave it right there. Alright, so there's a needle split. A weird needle split because it looks like engine 1 and 2 are keep trying to marry back up again. I'm going to add a little bit more. Again, when I add more throttle, we get a greater needle split, which is kind of weird. I'm not exactly sure what that's all about. Alright, moving on to the next section here. You can see we've changed scenery, and we went back to Lake County in, I think we're in Colorado. So we're going to do our some high altitude testing here, just like we did in the X-Trident 412, and this is the same airport we were at in X-Plane for the X-Trident test. So we're at Lake County Airport. Elevation is about 9,930 feet, 33 feet, something like that, so we're pretty close to 10,000. We're just going to call it 10,000 feet. Temperature is 20 degrees outside, winds are calm, and aircraft weight is 10,000 pounds. And if you remember from the last video, we set these conditions to make sure that we are power limited. So we're really high, it's kind of warm outside, kind of warm, 68 degrees, but it's not really that warm. But still, it's pretty high DA, and I made sure that I loaded the aircraft to a point where we should not have OGE power. So when we make these approaches, we're making the approaches with IGE power only. Okay, so we're going to check a couple of landing profiles and see how realistic it is. So hopefully, wow. Okay, so ooh, look at that. Okay, so we are pretty high on the power already. So clearly I've met my power restriction requirement. And this aircraft seems to be performing a little not as well at high density altitude and high gross weight as the X-Trident model did. But it looks like we're still going to make it happen. Alright, so we're going to come back around and shoot our approach to that helipad there. And the idea is we're going to do two approach profiles. We're going to do a shallow approach and a steep approach, and see if we get ourselves into any trouble. We'll bring in a little bit more power here, I guess, applying. So we're pretty much going to be focused on the left side of the torque, the mass, because we're going to reach our mass torque limit well before we reach our engine torque limit. And that's really what's going to be limiting our power. That's really what limits our power all the time when we're dual engine in this model. But we're going to pay more attention to it today, because that's the limit we're going to exceed first. Looking at our N1 numbers, we're pretty high on. I'll point to it for you guys because I have my hands here. We're already pretty high on N1, which means our compressor is working really hard to get power to the engines, and we're already really high on torque. So it looks like we have our conditions set up pretty well for this test. Now we're going to see. That's interesting. Wonder why that happened. We got a sudden dip in RPM. That's weird. Okay, I got too slow way too quickly while I was explaining that, so I'm going to try to build up some of this airspeed real quick. Bring some of that power back in. Alright, so we're going to shoot an approach to that helipad there. And see how things work out. Alright, so we're going to do the first one slow and shallow. I'm already slow. Looking at my rate of descent. So I'm already right at translational lift, if not a little bit below it. And I've got my VSI pretty much zeroed out, so almost zeroed out. We've got about a 200 foot per minute rate of descent going on, so that's pretty shallow. Looking at the engine instrument, everything looks pretty good. Everything looks pretty good. Increasing the rate of descent just a little bit. Airspeed dropped off a little bit more than I would have liked, but I'm already seeing the problem we're going to have here. So I'm going to zero out the airspeed just to see what's going on. And just as I suspected, we have OG hover power, like a lot of it. Oh, maybe not. Maybe not. Bringing that power. Okay, maybe we don't. Nope, looks like we don't have a huge power margin, but we do have OGE power. So I was able to bring it to a hover right at the top of the green arc on the torque limit. But that you can see that VSI is at 0, so we do have OGE power, just not a lot of it. We don't have much of a margin. And N1 is almost pegged. Okay, so that means we're going to have to add a little bit more to do the test that I want. So, I'm going to go to aircraft. I'm going to add a little bit more. I'm going to change our payload a little bit. So we're going to add about, what do you guys think? Let's add 500 more pounds, because we're going to go big. We're going to go big on this. Okay. So 10,500 pounds. We'll see how that works. I think we had a similar issue with the X-Trident 412, but we had to modify things. But I wanted to start the same parameters and see how this aircraft performs. So clearly the number crunching I did wasn't accurate. So we're going to increase. We already increased the numbers to try and get what we want. Alright. So we're going to come back around and try to shoot our approach to that same helipad. We're going to keep it shallow, keep it slow. Let's see. Now with that extra 500 pounds, I'm going to do a quick test here. We shouldn't be able to maintain an OG hover. climb in here a little bit. That should go away here. Okay, now that's interesting. Alright, so notice one thing here. I can't over-torque this helicopter. And when I say I can't, it's not that it's just so powerful that I can't over-torque it. The collective is all the way up, and oh, so maybe I spoke too soon. I did speak too soon. I damaged it. Look at that. Okay, so I can do something to it. So that's interesting. We're going to keep that in mind. Kind of wish we had some warning lights to go along with that. But alright, that's interesting. So here's one thing I noticed, and that's what I was about to tell you before things literally came apart, is that the collective all the way up, the torque stops right at the top of the green arc, which is, I'm going to go ahead and say it, that's not necessarily realistic, unless it just so happens that that was all the power I could possibly pull, and it just happened to stop at the top of the green arc. But I suspect that is not the case. But either way, we did have a rated descent at max power, so that means we don't have OG power. So I think this weight combination is going to be good for what we're looking for. We just have to try to adapt for that artificial power limit. Now, I'm not sure if I broke something, but the rotor RPM and engine RPM did rapidly decay as if we had a dual engine failure. So, would we get a dual engine failure for doing that? Probably not. Would we get a rotor RPM droop? Absolutely, as the engines began to limit. And I would expect our ITT to get higher, but for some reason it wasn't. Yeah, pulling max collectives all the way up. It stops right there at the top of the green arc, and the engine temperatures were pretty much right there in the center of the green. So I'm sure we're not going to be ITT limited. So engine temperatures aren't going to be a thing. It's just going to be, and it's kind of hard to say that we're torque limited because I'm full travel on the collective, and the torque will not go out of the green no matter what I do. And collective's all the way up. So I'm not even sure, to be honest guys, I'm not even sure I can test this. I'm going to try it anyway. So we're going to come back around, we'll slow down a little bit, set up this approach. Alright, short final for that helipad. Got a pretty decent rated descent here. Still somewhat shallow, and we're still somewhat fast. I'm going to slow it up just a little bit. And looking okay. And one thing I've noticed as I move the collective up and down, I am not seeing any fluctuation in the ITT. So that's kind of telling. And that may just be a code thing. It might be an FSX thing. Keeping it shallow. Power looks good. Rate of descent looks good. This should be pretty easy. We'll transition. Already coming through effective translational lift. Looking at the airspeed. Looks like we're well less than 16 knots. Bringing in some power. Should already be IGE, so we should be looking for IGE power now, which, looking at the torque, that's about where we're at. Alright, so that looks pretty good. Now let's try, we're going to do it again, but this time we're going to try a steep approach and see what happens. And this is what I'm kind of worried about, because it looks like it won't let me over-torque it, and we're not going to get a rotor RPM droop, so this is going to be kind of interesting to test. Alright, so up we go, and this... And we're going going to stay down close to the ground because we are actually power limited, which is a good thing. Just what's limiting our power is kind of confusing. Alright, clear out to the left. A little bit more power. And we've got... Yeah, so for the amount of power that we have in, I mean, we're right at the top of the green arc. We don't have any changes in the... no changes in the ITT and the engine temperature, so that's interesting. Alright, so we're going to try a steeper approach. And this one's going to be pretty low airspeed, higher, not necessarily a higher rate of descent, but it's going to be a steeper approach, and this should require a little bit more power to do in that shallow approach. And I suspect, well, I'm not going to suspect anything. We're just going to do it and see what happens. Alright, so already at a higher power setting, I want to climb. Alright. Since winds are calm, we can initiate this approach with pretty much any direction, so I'm just going to start from here. Alright, so I don't expect to get into much trouble until the end. Actually, we're looking pretty good. And actually, based on what happened last time, should be okay in that transition into IGE. And this was actually pretty steep. 500 feet per minute is probably a little bit too much, especially for as much power as we have available. We don't have a lot. So this would probably make me a little bit nervous if I was doing this in an actual aircraft. Because I probably wouldn't have a whole lot of extra power to arrest that rate of descent. This is probably a more comfortable descent angle. So not much of a difference really. Okay, so here's where we're going to try to find out what we got here. Alright, so pulling power all the way up. So this is actually looking pretty good. This is actually what I would expect it to do. And yeah, we're about IGE now. Yep, this is about right. So we got the collective all the way up. But here's the problem. So I would have expected either to get into this transient range here, and either have the rotor RPM start to droop, or see the ITT go pretty high. We're not getting either of those things here. What we're getting is the collective hitting the stop, the torque staying in the green no matter what I do. So that's not very realistic. So the power requirement is realistic to a point. It's realistic until we get to the top of the green arc of the mass torque, and then everything seems to get ignored right there. So that's can't really say that's realistic. That's actually very unrealistic. So can't really give full points for that. All right, guys. So for section 1.2.4. I think we already saw that we don't really have any warnings or caution lights when we had that sudden engine failure. So we're going to already count that as no points. And you probably already saw me flash the points up for that one already. So we're going to move on to the next section, and we're going to talk about some torque readings. Okay, so what we're going to do, we're back here on, I think we're on 3.5 left. Nope, we're on 3.5 right. And we're going to look at the torque required, because I already know what our torque is at an IG hover. I'm just going to go ahead and pull this up here. And we're going to compare that to the torque required at an OGE hover. So once again, we're going to come up to about a 5 foot hover-ish. looking at torque right around 60. Okay, so we don't weigh the exact same as we did earlier. I just kind of threw some weights in here just so we can look at something a little different. So we're at right about 60%. So now what we're going to do is we're going to go up to an OGE hover and see if there's any difference. Okay, so key instruments here is going to be the torque gauge there and our VSI, because that's going to show that we're actually at a hover. So we're going to pull in some more power. We got climb power in, and we're also keep an eye on our radar altimeter down here below. I'm going to pull in a little bit more power because I want to climb. Alright, this should be sufficient to be genuinely called OGE without any, yep, can't dispute that. We're OGE. Okay. So taking a little bit of this power out, I'm going to zeroize that VSI, keep the hover nice and steady as we possibly can. And okay, so there's definitely an increase in power required to hover OGE, but it's not much. It's about 5%, which I would expect a little bit more than that, to be honest with you, because we were hovering about 60, so now we're about 65. So let's look at, just confirm that one more time. I'm going to come back down to a IGE hover. Alright, so once again we find ourselves IGE. Okay, well at this time we're actually a little bit below 60, so we're almost at about 57-ish. So in that case, that's actually pretty good. So 57 and about a 7% increase. That's about 8%. Let's get OGE again. Alright, we're at 100 feet, definitely OGE. We'll go just a little further, just so there's no dispute. 150. Zeroing out the VSI. Alright, well, okay. So now, maybe that was my problem last time. So now the VSI is actually at 0. Oh no, we're looking pretty good here. So yeah, that's actually not too bad. So about an 8% increase in torque to maintain OGE hover. Yeah, I'll call that good. So VSI is at 0. We're OGE. We definitely got a torque increase. So yeah, we'll call that realistic. I'll take it. All right. So we'll give them 2 points for that. All right. So next thing we're gonna do is we're gonna transition to forward flight. And we're gonna check RPM reaction from collective inputs. So, and this section is pretty much all about the collective. Okay. So we're going to see how RPM is affected by collective input. So if I just yank in the collective, we should see a drop in rotor RPM. If I drop it, we should see the rotor RPM climb a little bit. And we already messed with this a little earlier, so I kind of already know what to expect here. But we're going to test it because that's what we're supposed to do. Alright, so we're going to get in level flight here in the downwind, modified downwind, we'll fly over these hangars, but I don't think anybody's going to complain. Alright, so about 70 knots, looking good, VSI is level. Alright, now I'm just going to yank up on the collective. Alright, RPM doesn't do anything. Lowering the collective. RPM does nothing. Okay, so, and we can see again, this is where we're looking at the attack in here. It's not really doing anything as I move the collective up and down. So we can see our torque fluctuate, but the rotor RPM is doing nothing. Okay, so we're going to bring it back around to 3.5. I think we were on 3.5 left earlier. Okay, our bad. Anyway, we'll try the same thing out of hover, where we should have a little bit more. We'll have a little bit more power applied. But I suspect we're going to see the same thing. So here at a hover, pulling up on the collective. Nope, nothing. So either this is the best governor ever, or this really isn't modeled all that well. And I suspect that it's just not modeled that well. Okay, tap the ground there a little bit. No big deal. Okay, moving on. All right, next thing we're going to look at is our rate of climb performance. So what we're going to do is we're going to, what we've done is we brought the aircraft back to 9,000 pounds. We're using the same parameters that we used for the X-Trident Bell 412 that we did in X-Plane in the last video. So we're back at Henderson Airfield. All those conditions are the same. Same density, altitude, pressure, altitude, same. Temperature, still 20 degrees outside. We got a 9,000 pound aircraft here, sitting here on the approach end to 3.5 left. And what we're looking for is we're going to use 70 knots and torque of 90%. And with that, we should see a rate of climb of 2,200 feet per minute dual engine. Okay, so that's what we're searching for. So if it's close to that, we'll call it good. If it's not, if it's more than that, which I suspect it probably will be, but we'll see. Because FSX aircraft usually tend to be overpowered, but we're just going to set those parameters and see what we get. Okay, so here we go. So we're looking for a 90% torque, bringing the power in. Hopefully we'll see that torque needle on the mass side go above 80%, because that would mean we actually were limiting when we got to, oh, there we go, there it is. I'm going to bring the nose up just a little bit to get at 70 knot attitude, and there's 90% torque. Keeping at 90, nose up just a little bit more to maintain that 70 knots. It's actually pretty nose high attitude for 70 knots, but here we go. All right, so 70 knots, we got it. 90% torque, we got it. 2,500 feet per minute, that's actually not too bad. That's pretty close. It's dropping off just a little bit. We're going to keep that 90% torque in, and I'm speeding up. But that was not too bad. That was only off by about 300 feet per minute. So that's pretty close. It's not spot on, but that's close enough for me to call it realistic. I'll take it. So that's not too bad. Now, here's going to be the challenge. And I'm not sure if we'll be able to do it. So we're going to try it single engine. For single engine, for 70 knots and 58% torque on the engine side of the torque gauge here. So for that last test, we were looking at the mass side, or what my manual says is the transmission side. So we'll be looking at a max of 58% at 70 knots, and we'll be looking for 400 feet per minute rate of climb. So we'll see if we can get that. Now, to get that, we're going to have to figure out how to get this thing single engine, or if we actually can get this thing single engine. One thing FSX wasn't great at was multi-engine helicopters. They emulated like the startup, I think, okay, like this aircraft here does, but actual single engine operations, that might be a challenge for us. So we're going to see what we can actually do. Alright, so I'm going to try and find the engine submenu, or the throttle submenu. That's not it. That's not it. There it is. Alright, so we're going to bring back one of these engines, if I can. Okay, looks like we did. We brought back number 1. Okay. So we should be single engine here. So it looks like we're working just with engine number 2. So get that out of the way. All right, so we are single engine number 1 is at idle. Number 2 is still in the green arc. And we can see that these needles here have split up. So this is the side we're going to be looking for this time. So we're really going 58%. So keeping that needle just below the 60% mark. Same airspeed, and we're going to be looking for about 400 feet per minute rate of climb here. So let's see what we get. All right. Try up too much. There we go. 68%. Looking for that 70 knot attitude. Looks like in this case we may be underpowered. This so far is actually pretty good. Doing single engine with limit. I think we actually have more power available single engine, and I suspect we have all of our power available single engine. But we're going to keep confined to the testing criteria here. So we were still at about 68%, 58% torque single engine. We're at 70 knots. There it is. Got a little zoom there because I pitched the nose up. That's a little high on the rate of climb. So looking for 400 feet. It's the VSI is starting to settle. Let's see what it does. Well, that's actually not too bad. It settled pretty good. So 70 knots. Torque's right where we want it to be. I zoomed up a little bit, but it kind of settled right at 500 feet. Right at 500 feet per minute. So, yeah, I'm surprised, but I'll call that good. And this fluctuation is because I'm messing with the cyclic here. And I'm in a little bit of a turn. But 70 knots, that's good. It's settling right around 500 feet. That's plus 100 feet per minute. I'll take it. We can call that realistic. Now, do we actually have more power available than that? Yeah, we do. But that's okay. Those were the numbers I came up with using the manual, so that's what we tested it at, and it was actually pretty good. So we'll call points for that. All right, next thing, we're going to move on to the next section, and we're going to start looking at the cyclic response. Okay, so what we're going to do is we are going to first pick the aircraft up to a hover, and we're going to note where the cyclic is. And we're back to a regular configuration. Aircraft weighs just over 9,000 pounds, same conditions as everything else. So right now we just have it kind of the default load on this model. Okay, so Cyclic's really not too far displaced, which I don't have any time in the actual 412, so I can't tell what the actual cyclic displacement should be. But we're going to test if there's any cyclic displacement when we change the center of gravity of the model. Okay, so we're going to put the aircraft back down. That was kind of a firm plant. That's okay. All right, and now we are going to add some weight and see if we can get a change in the cyclic displacement. So we're going to go to fuel and payload, and we're going to change the payload. And so what we're worried about is this right here. So we're going to change the center of gravity. So center of gravity is nice and centered underneath the rotor mass. Actually, that's not really indicative, but you'll see what I'm talking about. Okay, so the only thing we have right now is just the 2 pilots. So we're going to change that. We're going to try a lateral CG change. So we're going to add some weight to the hoist. So we're going to add, let's say, what do you guys think? Let's do about 300 pounds. All right, so we should see some lateral CG shift
when we do this. Okay, there we go. All right, so actually that's not too much. Let's change that a little bit more. Let's go with 400 because I really want to see a change here. So it's kind of extreme, but not 3400. That's actually a little crazy. Yeah, so we'll go with 400. There we go. All right, so we have a lateral shift in CG. So the right side of the ship should weigh more than the, well, not weigh more, but have more weight on it than the left side. So what we should see is a definite change in the required power, or not power, but cyclic displacement in order to keep the ship level. Okay, so now that all that's being said, we're going to, I'm going to reset my view here because it's a little bit canted. There we go. All right. So now we're going to pick it up and see if that 400 pounds to the right makes any difference. So we took off, actually it looks, well, not really. So we took off a little bit of left skid low, but I think that might have been because of the way I had the cyclic when we took off. So we're going to put it back down and take off again. And got full throw on the cyclic. Okay. So back to center. Alright, so the aircraft tends to want to drift that direction, but not really much of a difference. So I would expect to have a little bit more left cyclic in to keep the aircraft removed, but now the aircraft is actually just pretty much just behaving the same way it normally does. So we're going to add some more weight. I want to see what it actually takes to get some cyclic displacement out of this, if we actually can get any cyclic displacement. So hopefully that'll be something we can do. Come on, you. All right, change payload. Change payload. So we're going to put, you know what? Why don't we, yeah, let's go big here. I know it's not realistic, but I'm going to give this, so that's a huge lateral CG shift here. So I want to give this model every chance it can to prove that it does model some sort of cycle. Oh, there we go. So we definitely saw the weight there, because with 1,400 pounds that far off, the aircraft is now sitting right side low. So it's physically sitting right side low. So hopefully that'll translate to some cyclic displacement. So, and that may have been why I thought my view was canted earlier, because the aircraft is now sitting right side low. So let's see if we can't get this to, well, let's see. All right, so bringing in some power. Aircraft leveled itself, which is kind of weird. I would expect the aircraft to continue to roll in that direction, in the direction of the heavy side. So that's not all that realistic. And as we pick up, okay, yep, I didn't touch the cyclic at all, and the aircraft is level. So, and we're actually even drifting the opposite direction. So that doesn't really bode well for this test as far as this model is concerned. So that's with 1,400 pounds offset. That's for it to take off, naturally roll, drift the opposite direction of the weight. Can't call that. There's no way I can possibly call that realistic. Now, I'm trying to feel if there's like even a minute difference in how much cyclic I'm using, displacing, and it's not. It's behaving pretty much exactly the same as it did without the 1,400 pounds off to the right. So can't call that realistic. No real points for that. So we're going to get rid of that weight, and then we're going to move on to the next test. Alright, so we got all that extra weight done, out of the way. We're back to our normal testing weight. And the next thing we're going to do is we're going to test translational lift and see if translational lift is modeled. So if you guys have seen my other videos, you know what translational lift is, and if you're watching this video, you probably already know what translational lift is, so I'm not going to go ahead and explain it. But we are going to keep an eye on our airspeed indicator, and we're going to keep an eye on our BSI. So we're going to be looking here, we're going to be looking here, and I'm going to be looking outside and hovering the helicopter instead of pointing with fancy hand pointers. All right, so basically what we're looking for is just that increase in efficiency for a given power setting. So I'm going to use the power that we have in now, so just about 55% torque, and just going to ease cyclic forward, and we're going to see if we can develop a positive rate of climb after passing through translational lift. So easing it forward, and this should happen somewhere between 16 to 24 knots, and we should see it feel a little bit of a dip, which maybe we're already at 40 knots. So not the best. Let's try it again. Let's try that one more time, because we just sort of accelerated really smoothly through. So what I would expect to see is just a little bit of a dip as we get through transverse flow, and then a nice efficiency increase in the rotor and get us a positive rate of climb. Now I could have just brought the Cyclic back, to be perfectly honest with you, and we would have got a positive rate of climb. But I'm just looking for those telltale signs of translational lift. Now, some aircraft would you'll need to do some lateral cyclic displacement because the aircraft will want to roll, but not all of them really do. So now we're passing through translational lift. We should be through it right about, well, we've already we blew right through it. So yeah, I mean, I'm not getting all the physical signs, which isn't uncommon for a simulator, to be perfectly honest. But for takeoff power, for IGE hover power, I've got a positive rate of climb. So I've got an acceleration, and I've got a positive rate of climb. All of that with takeoff power. So, not takeoff power, but IGE hover power. So I can't argue against translational lift because, well, the model is doing what it's supposed to. So, yeah, points. All right, let's go find some slopes. So we're gonna do slope landing, and hopefully these guys aren't mad that I'm flying over the ramp here. I don't care. Now the terrain mesh in FSX isn't as high res as it is in DCS and X-Plane. So this is my usual slope area right over here, but as you can see, it is very flat right here where these houses are. So this is where I usually test slopes. So we're going to go somewhere else. So I think up here near where FSX has a golf course, there might be a slope that's suitable for us. We'll probably end up sliding, but that's okay. We're testing the cyclic response, not the friction. Alright, so here we go. I'm going to come uphill just a little bit. There we go. Alright, there's a good reference point right in front of me. Just going to gently lower the uphill skid down to the ground. There it is. I said gently. That wasn't very gentle. Alright. And then as we lower the collective, some uphill cyclic. Gently. There we go. That's not too bad. That was pretty good. Now you can't really see much. There we go. Now the cyclic spot centered. So yeah, there was a pretty good amount of cyclic displacement there. So we'll test it on the as we climb up. We're already starting to slide as I bring in power, so I'm going to bring in a little bit of right cyclic. There we go. And then lift the downhill skid off the ground. A little bit of left pedal. Yeah, that feels pretty good. that was pretty good for a slope landing. I would, and even that's a pretty extreme slope, but yeah, that worked. I'm inclined to give full points for that. We'll try a toe-in skid, toe-in, which we're definitely going to slide backwards and probably going to smack the tail rotor on something, but whatever. This aircraft's free. Alright. Got the toes on, some forward cyclic. We lower the heels. Not bad. Not bad. Yeah. Can't argue with that. Oh, full points for the slopes. Full points for the slopes. That performed really, really well. All right, guys. So as we're gonna look at the next section here, we're gonna start wrapping this up. So I know it's a long video. So now we're looking at section 1.5.1, and that's just cyclic sensitivity. And this is actually pretty easy to evaluate because I'm a long time former FSX user. I use FSX a lot, like from when it came out to probably around 2014 is when I stopped using FSX regularly. And the cyclic displacement, like the cyclic sensitivity, control sensitivity, the collective is not too bad. Collective and pedals are not too bad in FSX. The cyclic, however, is the weak point, and this model actually suffers from a lot of the shortcomings other FSX models for helicopters suffer from. So the sensitivity is okay, and it's kind of hard to, I guess it depends on your definition of sensitivity. But the amount of cyclic necessary to get the aircraft to do what you want is way too much. So, and FSX aircraft tend to be overly stable. So like right now, I'm not moving the cyclic at all. And the aircraft just kind of sits here. But as we pick up this aft drift here, if I want to correct it, what would normally just take a little bit of pressure, like not even enough to register movement, fix it. Now I have to put in a lot more cyclic than I normally would to get it. So all of the control inputs are exaggerated. And even in normal flight, we'll take off and do a pattern here. So again, the pedals are just fine. Collective input, just fine. FSX's weak point, and this model is no exception, is the cyclic input required to get it to do what you want. So even here, I had to bring back a lot of cyclic just to bring the nose up. And larger helicopters tend to use more cyclic input. So FSX does tend to do better with large, heavy helicopters. But that's not even all the way true nowadays because of because of advances in flight control technology and engineering. But this model isn't as bad as some others. I'll give it credit for that. It's not as bad, but so to correct this roll, and the animated cyclic here isn't quite showing what my ProFlight trainer is doing, and this was okay back in the days where everybody had a desktop twisty stick, right? Because the fidelity of those controls were so bad, I won't say bad, but so low that you were doing these large control inputs anyway. So it all sort of just married up. But now with a product like the ProFlight trainer, this is extremely noticeable. And this is one of the things that caused me to virtually abandon FSX as a flight simulator, was the cyclic response and the amount of cyclic required. Because with if you have a ProFlight trainer, FSX, you might want to consider moving away from FSX because of this reason, because the resolution on the Cyclic is so much better. A lot of that is wasted in FSX because you're not getting the full, and let me show you here. I'm going full throw on the Cyclic. See that? That rate of that, so that's, that delay there is, I mean, yeah, there's some delay, there's some mechanical delay, mechanical and aerodynamic delay in helicopters when you do cyclic inputs like that, but it's not that much. I'm going to show you again. So I'm going to go full throw left and see that, and this is full throw. Pitches seems to be okay, but in roll that, and oh, see, I was holding that av cyclic there, and it took a long time for that nose to come back up. So pitch is a little bit better than the roll axis is, but even then, I'm doing these in any other model, in any other platform, I can do the same stuff without going full throw on the Cyclic. So that's, it's I can't really give full points for that. Okay, so the next section we're going to look at is any sort of special equipment, and for that we're going to set it down here anyway. We'll set it down next to the cetacean, or in front of the cetacean. So specifically vertical reference equipment, not much. So for an aircraft like this, if we're going to do vertical reference with, one, there's no real sling load capability here. What we do have is now there are some add-ons that you can get to create missions for sling loading. We're going to look at the sim here. Aircraft. So what this has is, let's go large desktop view. Okay, so as far as special equipment, there's nothing here specifically for vertical reference and doing sling load stuff. But what this model comes with is all sorts of different variants, right? So unlike in X-Plane, where you can modify through a modify each model, this one just you can't really switch it up. You just pick the model that's equipped that you want, that you like. Which again, this comes from Microsoft Flight Simulator 2004 Century of Flight. So the technology base is a little different there. So if you wanted no doors, you'd have to pick a no doors model. Offshore model, I'm not even sure they have. Yeah, some of them have floats equipped. Nothing real specific for vertical reference long line flying, just sort of general. And I'm not even sure about the operability of a lot of these add-ons. There's a military one, but I'm not sure. Yeah, and like there's no really operational FLIR or anything like that. And there is, like we saw the hoist. There's some of these are equipped with a hoist, but really all you can do is just add weight to it. So as far as special equipment goes, yeah, special equipment is available as far as being used essentially cosmetically, and like there's like the radome on the nose for some of these models and things like that. So there is some special equipment available. However, it's not exactly, shall I say, useful. Now, for vertical reference stuff, I would expect to see like a bubble window or something like that. Like the X Trident model, you actually had sling load capability, so that was fun. But this one, you don't really get any of that, and none of that stuff really existed when this model was created. So can't really give them points for that. All right, to wrap it up, guys, this model has definitely shown its age, and as far as flight dynamics wise, it was great. I mean, it was the pinnacle for Microsoft 2004, and it held up okay in the FSX days, and it was updated. This is the version specifically for FSX. But when compared to some of the offerings in in X-plane and DCS, it's probably lacking, especially comparing to other aircraft in this category. So in medium helicopters, which is what we're comparing here.